Okay, so I'm moving on with Abelian von Neumann algebras. And what's going to happen now is that we're going to talk about cyclic and separating vectors, which is sort of a technical tool for what we're going to need to work with. So here are two definitions. So we will let A inside B of H be a subsystem algebra, and X be a vector in H. And we say that X is, so here are two key definitions. It is cyclic, and I guess it is cyclic for A to be precise. If the set Tx with T coming from A is dense in H, and we say that it is separating for A if the map T goes to Tx is 1-to-1 on A. So these are two kinds of nice vectors, if you like. A cyclic vector has the property that if you apply all the operators in A to X, then you get a big set, something which is dense in H, and X is separating if it has the property that it sort of can be used to tell the elements in T apart. So the map that sends T to Tx is going to be injective, right? So that means that if you have two operators in A and they act in the exact same way on X, it's because they are the same. And we need a lemma, which is interesting in its own right, but we're only going to use it in the context of Abelian von Neumann algebras. It goes this way, so let A, just like before, be a sub C-star algebra. And X is in H. The theorem is that X is cyclic for A, if and only if X is separating for A prime. So to prove this, let's go from the top to the bottom. So assume X is cyclic for A, and that Tx is 0 with T in A prime, right? Then the goal is to prove that T actually is 0, and hence we have proved that X is separating. So note for any S coming from A, we have that when we apply t to sx, that is the same as stx, right? Because t comes from a prime, s comes from a, so they commute. And by assumption tx is 0, so that is 0. So tsx is 0 for all sx with x in A. But the set of sx's with s in A is dense in H, because we assumed that x was cyclic for A. So t is 0 because it vanishes on a dense set. Okay, so that takes care of the downward implication. So in the other direction, we assume x is separating for a prime. We will let m equals the elements of the form tx, where t lies in A, closed off. So the vectors of the form tx with t in A is going to be a subspace. So when I close it off, it's going to be a closed subspace, which of course lives inside H, right? And the goal is to prove that that actually that is all of H, because then we've proved that the elements of the form Tx form a dense subspace of H, which is what we need to see that H is cyclic, but we're not quite there yet, right? So note that X is in M, since the identity lies in A, and that when I apply T to M, I get inside M, and when I apply T star to M, I get inside M for all T coming from A. This follows just by the definition, because if I'm applying T1 to T2x, that has a form T3x, where T3 comes from A, and a star is fine as well, because by assumption A is a sub-C-star algebra, so it's closed under stars. We've done this argument before in another context. So this means that M is what we've called reducing for A. So the corresponding projection P lies in A prime. Right, so this is one thing that we've proved in general. So now note that px applied, I mean, what is px, right? Px is going to be x because x lies in M. This was the assumption that, or the observation that I did up here, right? So since P is the projection down on M and x is in M, when I apply P to x, nothing happens. But of course that's true of the identity operator as well. So since both P and I come from A prime, and x is separating for A prime, we get that those two operators are the same. So this means that P is the projection, which is the identity. So that can only happen if the space that we're projecting down on is all of H, which is what we wanted to prove. So a corollary of this is suppose A and B of H is abelian, then X is cyclic for A implies X separating for A. There's no prime on the second A, right? And the proof is just that we've seen that A lies inside A prime. So if X is separating for A prime, it is also separating for A. Right, so it means that, at least in the context of abelian subalgebras of B of H, it's a stronger property to be cyclic than it is to be separating. And so we end up by proving a technical result that we will need a little bit down the road. I'll call it a theorem, which is sort of in this context. So if A lies in B of H is an abelian sub C star algebra, and H is separable. So my Hilbert space cannot be too big for this to be true. Then there is an X in H which is separating for A. So I'm claiming that I can always find a separating vector for a commutative subalgebra of B of H if H is a separable Hilbert space. So proving this is a Zorn's lemma argument. So let's write mx to be elements of the form Tx, where T comes from A. So these are the kinds of subspaces we've looked at before. And consider a set E, which is a set of subsets of the unit ball of my Hilbert space that has the property that mx is orthogonal to my for all x and y in E, of course, different. Right, so what I'm trying to work with here is a collection of vectors of norm 1 or less with the property that when I take these two subspaces mx and my, all the vectors are going to be mutually orthogonal for choices of x and y that are different. Right? And we can apply, so it's easy to see that E is non-empty, and any linearly ordered subset under set inclusion has a majorant. So hence Zorn's lemma applies, right? So first of all, why is it not empty? Well, I could just take the set consisting of a singleton that will, of course, satisfy the relation. Why does it have this property that we need in Zorn's lemma of having upper bounds for linearly ordered subsets? Well, we can simply take, if we have a collection of such E's, we can just take the, so that either E1 is contained in E2 or E2 is contained in E1 for any pair. We can just take the union and that will satisfy the relation as well. So we have the conditions of Zorn's lemma. So trusting in the axiom of choice, there is a maximal element in E. So we can fix E naught a maximal element of E. So note now that since we have units contained, the unit is contained in A, all elements in E naught must be, they must be mutually orthogonal, since x lies in mx, mx is orthogonal to my, and that contains y. Right, so the elements in E naught must be mutually orthogonal. I guess 0 is in there, right? So 0 element lies in there as well. That's fine. But we note that by our assumption that H is a separable Hilbert space, we conclude that E naught is countable. We also see, we note also that if we take the union of all the mx's with x in E naught and close it off, we will get, what am I trying to say here? Right, I guess I'm doing this wrong as in the book, so let me write it correctly. What I really mean is that if I take the sum of all the mx's with x ranging over the E naughts and close it off, I will get H, right? And that follows by, so since if y was orthogonal to all the mx's with x in E naught, we and y was not the zero vector, we could add y to E naught and get a contradiction to maximality. So, I mean, essentially what I know now is that I take all the elements in the E naught, I take the span of the mx's, they will be, the mx's will be mutually orthogonal subspaces. I add them all up and I get something which is close, which is dense in H, right? And the idea is that I want to get from this that I can create a separating vector. So let E naught be written as xn with n in n, right? So it's countable, so I can do that. And then I will let x be the sum from 1 to infinity, 2 to minus n, xn. Right? And this lies in H because these are mutually orthogonal vectors, and I put on weights on it so that this will become summable. My claim is now, of course, that X is separating, so fix now a T that lies in A, and assume that Tx is 0. Then the idea is to convince ourselves that T must be 0. So, but what does that mean? It means that Tx, which is, T applied to the sum, to the minus n, xn, is 0. And that is the same as the sum n equals 1 to infinity 2 to the minus n txn. But notice that all the txn's come from mxn, right? Because t comes from A, and so txn lies in mxn. And we know that these mxn's are mutually orthogonal subspaces. So that means that the txn's have to be mutually orthogonal. So since I know that txn is orthogonal to txm for m equal to n, we conclude that actually txn equals to 0 for all n. Right? And now this means that if we look at t of s xn, where s comes from A, then because we've assumed that everything commutes, that A is abelian, that's the same as stxn, which is 0. Right? So t vanishes on all the mxn spaces, and hence on all of H. So what I've done is I have created a separating vector for any abelian subalgebra on a separable Hilbert space, and you can see it's sort of straightforward if you believe in the axiom of choice. But as we'll see later, this is a key ingredient in explaining what the abelian phenomenon algebra looks like.